Everyone. I'm Kevin, and today I'll be presenting XIRL, Cross-Embodiment Inverse RL. This is joint work with wonderful collaborators Andy, Pete, Jonathan, Jeanette, and Debbie. So the goal of this work really is we want our robots to watch us humans perform tasks and then learn how to do them. But before I talk about that, I want to talk about why have robots watch humans, and what is this cross-embodiment problem that I mentioned in the title? And the reason we want to have robots watch humans is that in typical imitation learning scenarios, you usually need to have experts teleoperate the robot to collect data. And this can be quite time-consuming and unscalable. And if you have such a setup that requires specialized hardware to do, then you typically have, your progress on the project will kind of look like this, where the amount of robot learning is kind of throttled by the grad student, and the availability of the hardware. So for example, you could forget to log the data, or you delete the data because you change your end effector. And so this isn't really scalable. What we really want is to have a curve that looks like this. And we believe the way to do this is to have robots that learn by watching. And if we can unlock this capability, then anyone can show demonstrations to the robot, and we don't need specialized hardware when we do the demo collection. And eventually, what we really want is robots that can learn by watching YouTube videos, for example. Unfortunately, the main limitation of third-person visual imitation is this issue of the correspondence problem. And if you think about this dog trying to imitate the human at opening the door, you could try to manually hand-define correspondences between the dog and the human. But you'll quickly find that trying to hand-define these correspondences can be sometimes impossible to define. So think about how you would try to define these correspondences for an octopus trying to open a peanut butter jar if you have a human demonstration doing it. And sometimes, even if there is a clear-cut correspondence between the two embodiments, there might be physical constraints between the learner and the demonstrator, which make it futile to define. There have been previous works that tackle this cross-embodiment problem, either by doing explicit domain adaptation, but that introduces visual artifacts. And other previous works do indeed use manually defined correspondences, but as we just mentioned, this can be limiting and sometimes impossible to do. So to reiterate, in a typical imitation learning pipeline, both the learning and the demonstrating happen on the same hardware. So you have a clear-cut mapping between state action tuples from one domain to the other. But really, real intelligence can imitate with different strategies despite different embodiments. And especially in the case of robots imitating humans, because the end effector is morphologically different than the human hand, you're going to run into this problem where the robot just can't do the task the way the human does it. And so if we think about this door opening task for a minute, we can realize that it doesn't really matter how the door is open. What really matters is that it is open. And so the question we ask in this work is whether we can learn a notion of task progress that is invariant to the embodiment performing the task. So we do this in 3 steps. The first thing we do is that we self-supervise a reward function. And the way we do that is we learn an encoder using expert demonstrations of different embodiments performing a task. We learn this encoder with a temporal cycle consistency objective, which learns the task progress and encodes it in the embedding, and I'll talk a bit about that later. Once we learn this encoder, we can use it to define a reward function. And the way we do that is that we take the embedding of the current observation and we measure its distance in the embedding space to the mean goal embedding. And then once we have this learned reward function, we can plug it into a reinforcement learning algorithm like SAC and learn the behavior on the learning agent. So the way we encode this task progress in the feature embedding is we turn to this a recently introduced self-supervised pre-training method called temporal cycle consistency, or TCC for short. And what TCC does is it learns to align videos of different agents performing a task to temporally align them. And it does this by maximizing mutual soft nearest neighbors in the embedding space. And the authors showed that when you perform this unsupervised video alignment pre-training objective, you learn a very nice structured embedding space where the trajectories overlap in this embedding space. And our intuition is that it should be possible to encode task progress in this embedding space. And in fact, we did take this data set that I'll talk a bit in a minute. We took this data set of different agents performing a manipulation task, and we look at the embedding space, and we also look at the reward function. And we can see that the reward correlates nicely with task progress as the agent is performing the task. So to examine this cross-embodiment imitation setting, we introduced this kind of like MNIST for cross-embodiment imitation, which we call XMagical. So XMagical is a simulated benchmark. It's based on a 2D physics engine, so it makes it very fast. You have very high FPS, so quick iteration. It's easily extendable. You can add new embodiments or new tasks, and it has a gym-like API. So I encourage you to check it out. But we focused on this sweep to top task in the environment. And here we have 4 different embodiments, 3 stick agents and 1 gripper agent. The stick agents have 2 degrees of freedom, and the gripper agent has 3 degrees of freedom. And here the goal is to sweep these debris to the top of the arena here in the pink zone. And what you see is that by changing the shape of the agents, you kind of change the strategy and the way they perform the task. So if we look at demonstration data that we collected and we plot the state distribution that the agents visit in these expert demonstrations, you'll see that for an embodiment like the long stick, it's just a very simple linear trajectory to complete the task. Whereas for more complicated agents like the short stick and the gripper, they have a much wider coverage of the state, and you can look at the trajectories on the right here, randomly sampled trajectories, and see how different they are than for the long stick agent. And so the first question we wanted to ask was whether reinforcement learning could work with our learned reward. And so the setup here is that we train our reward on demonstrations of one agent, and we perform reinforcement learning on that same agent. And here what we want to see is that the challenge here is that our encoder should generalize to states that were unseen in the pre-training demonstrations. And what we see is that across the board on all 4 agents, our method results in more sample efficient policies. So note that all these curves here use the same RL algorithm. It's just the reward that changes. And so our policies, especially on the harder agents like the short stick and the gripper agent, perform significantly better than baseline alternatives. In a setting we care more about, which is take this reward and generalize to unseen embodiments. So what we do is we pre-train the representation on 3 embodiments, and then we perform RL on an unseen held out embodiment. And we do this for all 4 different combinations of this. And again, we have the same storyline here where across the board, we perform better than baselines. Our policies are more sample efficient and perform significantly better on the harder agents here at the bottom. On a real world challenging setup as well, where we pre-train the reward on human demonstrations and then transfer to a simulated robot for a puck pushing task. Same storyline as well. Our policies here in red perform much better than baseline alternatives and using the sparse environment reward. For some qualitative results, so the first thing I wanted to look at was what do our learned rewards look like? And so here I'm specifically teleoperating the agents and plotting the learned reward. So as you can see on the left here for the XMagical benchmark, comparing the positive demonstration to a negative one, you can see that we assign much higher reward for the positive demonstration than for the negative one, and it correlates nicely with the task progress. And specifically here on the right with the Sawyer arm, you can see that for this negative demonstration where the agent arm overshoots, the reward starts to decrease as well, which is great. We also collected a data set we call XIRL. We have 9 different embodiments. Some of them are shoppable on Amazon. And we perform this pens in cup and mug task, where you first have to pick up the pens, place them in the mug, and then take them out of the mug and place them in the cup. And what we see is for pathological demonstrations, like here on the right, where the global movement is the same as what you would do for a positive demonstration, but you don't grab the pens, you fake it. It assigns much lower reward than for the positive demonstration. In this case, the difference between the top row and the second row is that at the end, I'm sloppy with placing the pens in the cup and some of them fall out. You can see that the reward dips as well. So the reward is able to capture these fine-grained details. For this task here, the difference between the positive and negative demonstration is that the negative only does half the task. So we only place the pens in the first cup. So you see the reward in orange here increases, but then plateaus, whereas for the positive demonstration, it increases. And so the main takeaways here, I introduced the cross-embodiment imitation problem, and I showed that especially for robots imitating humans, you're gonna face this cross-embodiment problem. And rather than trying to define correspondences from one domain to the other, what we do is we learn a reward function that is embodiment invariant, and that encodes task progress. We showed how we can self-supervise this reward using a temporal cycle consistency objective, and that a simple reward formulation that doesn't use any time indexing or test time alignment can result in very sample efficient policies that beat baseline alternatives. Thank you.
Thank you, Kevin. We have an online question from Steven Chuang. What if the expert embodiment differs drastically from the test agent? Any experiments? So to put differently, how much can you actually push the difference in embodiment?
Yes, that's a great question. So the assumption we make in our work is that across different embodiments, there's going to be states that are intrinsic to the task that most embodiments are going to visit. And so in the case where you have something completely different that doesn't do anything remotely close to what you see in the expert demonstrations, I don't think that our method would give any reward signal in that sense. So yeah, the assumption is that most embodiments, they're going to be different, but there are some states that they visit that are similar, and that's what TCC is exploiting and aligning.
Yes, question over here.
Hi. Yeah, I was just curious how, if you have compared with GALE, the generative adversarial imitation learning, when using only states.
We don't compare to GALE. Most of our baselines are things that use reward learning methods. So there's TCN, time contrastive networks. We have a goal classifier which learns to classify whether an image is the goal state or not. But yeah, no explicit GALE.
Do you have an intuition?
I think it would do well, but especially on tasks where, for example, when you try to transfer from stick agents to gripper agents, I think that's where our method would shine and provide, like the dense signal you're getting from the XIRL reward would perform better.
Hey, very cool project. So I'm wondering, how did you get the expert behavior for that sweeping task with all the different embodiments? It seems pretty non-trivial. Is it like a human that's kind of doing it or something else?
You could do that with a scripted oracle, but the way we do it is, define the mean average reward. So like hand define a reward function, train an SAC policy, and generate the expert demonstrations.
Okay, makes sense.
Okay. Oh, one last question. Good.
Sure. Kevin, I was wondering, you showed in the humans demonstration videos that the human was pushing the puck at a very gradual pace and making sure not to like occlude the puck and everything. So some of these things might be obvious, but could you explain to us what would be hard about imitating a video where the human just did like a natural motion without worrying about occlusion and everything, and why it would be hard?
So you're asking what would happen if you do an unnatural movement?
Rather, you do a more natural movement, like you just kind of push the puck like you normally would, like you weren't doing this for an experiment for a robot demonstration.
So I don't know if this answers your question directly, but when we do the pre-training, we do like really aggressive data augmentation, and one data augmentation we do is cutout, where you like randomly black out a square in the scene. So effectively, we did that for the puck pushing task, and you randomly, like there's parts of the scene, the end effector, that completely disappear, and that helps the reward learn to focus on things that matter for the task, not the overall hand movement, but more, is the puck inside the goal zone or not? So I think that, there might be instances in your demonstration where you have something unnatural or you have partial observability, but I think that's good. And these are things that that can help you learn a better reward function.
Great. Okay, thank you, Kevin. Great talk.
Thank you.
Let's thank all of our speakers from this session. Thank you, guys.